You are answering the lesson question, how are rotations defined mathematically? You've examined some key aspects of rotations. For example, they are rigid transformations that preserve shape and size. Now let's continue the exploration of this type of transformation.
You've just explored some of the attributes of rotations. And now I think it's time that we discuss the formal definition of a rotation. In a rotation, each point on a figure is turned through a given angle. So the points are rotated in a given direction, either clockwise or counterclockwise around the center of rotation. In this example, the center is this point. The center of rotation can be anywhere. It can be anywhere inside, on, or outside the figure. You can think about a rotation as a rigid transformation, sometimes called an isometric transformation, that moves every point of the pre-image through an angle of rotation around the center of rotation to create an image. The points move in a circular direction. When angles of rotations are counterclockwise from the center of rotation, the angle is positive. Now, if the figure is rotated clockwise, the angle of rotation is negative. Note that in this example, if the rotation was counterclockwise, the angle of rotation would be positive 180 degrees, and if it was clockwise, it would be negative 180 degrees. The distances connecting corresponding vertices to each other are not the same. Let's go ahead and draw in these distances. So we have one from B to B prime, one from A to A prime, and one from C to C prime. And see, when the angle of rotation is 180 degrees, they all pass through the center of rotation. These line segments are not congruent. They're not all the same length, nor are they parallel as with translations. However, the distance between each point on the pre-image and the center of rotation, so this, for example, is the same as the distance between the corresponding point on the image and the center of rotation. This is true for any point on the figure. And always remember that all points on the figure are rotated, not just the vertices. So we can draw a line from this point on the pre-image and rotate the line 180 degrees to arrive at this point on the image. And we can see that the distance from that point on the pre-image to the center of rotation is going to be equal to the distance from the center of rotation to the point on the image. Because this is a rigid transformation, remember that size and shape are preserved. If the angle of rotation had been 360 degrees rather than 180 degrees, the figure would have been mapped to itself.
When we rotate a figure, we do so around a center of rotation given You are doing a wonderful job working towards answering the lesson question, how are rotations defined mathematically? We have defined rotations given an angle of rotation and center of rotation, examining the properties used for constructing images. Let's consider a rotation like the one shown here, and how we can define rotations in the coordinate plane with the center of rotation at the origin. We will now examine rotations in the coordinate plane. The same properties hold, but now we can consider the coordinates or ordered pair of the vertices to help with determining the location of the image given a pre-image. Consider the pre-image ABCD shown here with center of rotation at A or 0, 0. If we rotate this parallelogram 90 degrees about the point A, we will produce parallelogram A, B prime, C prime, D prime. Now, since the center of rotation is at the vertex A and A prime would have the same position. Since the center of rotation doesn't move, we can call the parallelogram A, B prime, C prime, D prime. Let's take a closer look at this rotation. Consider vertex B, which is at point 2, 0 on the x-axis. We can draw a line from this vertex to the origin, noticing that it's 2 units long. And then if we draw a line 2 units long up the y-axis to create a 90-degree angle and congruent corresponding lengths, we arrive at B prime with coordinates 0, 2. We could check each point, other than the center of rotation A, which does not rotate, to get the image A, B prime, C prime, D prime, connecting corresponding vertices to the center of rotation would show that the angle created is 90 degrees. So let's do the same thing for vertex C. We'll draw lines connecting C to the origin, and then connecting the origin to C prime. Now when we do this, we see that the angle created is 90 degrees. We see that vertex C at point 3, 2 maps to point C prime at -2, 3. And then we can also see that vertex D at point 1, 2 maps to D prime at -2, 1. Each have equal distances to the center of rotation, and the connecting segments all make a 90-degree angle. Can you see the pattern in the vertices between the pre-image and the image? It seems like the x-coordinates are switched with an opposite-signed y-coordinate. Let's formalize this pattern. There are special rules that can be used when considering the functional relationship of rotations about the origin. These rotations all go counterclockwise for positive angles of rotation, and these rules only work when rotating about the origin. So let's take a look at vertex A at 1, 4. We can see that if A is rotated 90 degrees, so here would be our origin right here, and then we go to A prime, making a 90-degree angle, then we have A prime at -4, 1. This rotation follows a rule. A rotation with a center of rotation at the origin and an angle of rotation of 90 degrees allows a coordinate point xy to be mapped to -yx. So if A is 1, 4, then A prime is going to be -4, 1. And if A is rotated 180 degrees, like so, then we have a rotation that allows a point xy to be mapped to -x, -y. So if A is 1, 4, then A double prime down here, after being rotated 180 degrees, is going to be -1, -4. And finally, if A is rotated 270 degrees, like this, then we have a rotation that allows a point xy to be mapped to y -x. So if we have A at 1, 4, then A triple prime will be at 4, -1. Note that the angle when rotating 270 degrees, it looks like rotating -90 degrees. And I'll point that out right here. But remember that we are rotating counterclockwise. A rotation of -90 degrees would go 90 degrees clockwise, which looks the same as a 270-degree counterclockwise rotation. Similarly, 90 and -270-degree rotations result in the same image. Also remember that a rotation of 360 degrees would bring the figure back to itself, since 360 degrees is a circle. We could repeat these steps to get the entire rotated figure for each of the benchmark angles of rotation and draw the corresponding triangles. What rule describes the rotation about the origin from the pre-image to the image? So we know that triangle QRS is the pre-image and that triangle Q'R', is the image. To answer this question, let's begin by looking at one vertex and its image. We'll pick vertex Q. So we have Q at 1, -1, and Q prime at -1, -1. We see that the y-coordinate stayed the same, but the x-coordinate became negative. From this point, it may appear that the rule is xy being mapped to -xy. But let's check the other vertices just to make sure. Well, we have vertex R at 4, -1, and we have R prime down here at -1, -4, which shows that if we have a coordinate at xy, that will be mapped to y -x. Now note that this rule also works for q at 1, -1, and q prime at -1, -1. So we can eliminate that first rule that we guessed. So we have vertex S at 4, -4, and we have S prime at -4, -4. This also shows that xy is mapped to y negative x. So the rule for this rotation is xy being mapped to y negative x. Now notice that we could also write this rule in this notation. And I'll explain the 270 degrees in just a moment. So we also want to know how many degrees about the origin was this figure rotated. Well, this is the rule for a 270-degree rotation. So we can say that it was rotated 270 degrees. So knowing this is how we got to this other rule notation. What is the image of triangle DEF after a rotation at the origin with an angle of rotation of 270 degrees? Well, a rotation of 270 degrees about the origin is a function that takes an input of xy and maps it to an output of y negative x. It rotates every point on the figure 270 degrees about the origin. So if we were to write this rule right here, we see that if we have a point at xy, it's mapped to y negative x. Let's use this rule to rotate the triangle 270 degrees, starting with the vertices. So we'll start with vertex D. Vertex D is located at -5, 2. And if D prime is equal to y negative x, then D prime is equal to 2, 5. So let's go to 2, 5. That will be where D prime is located. Now let's take a look at vertex E. Vertex E is at -1, 2. And if E prime is located at y negative x, then E prime is located at 2, 1. So let's go ahead and plot at 2, 1. We'll call this E prime. And now we're dealing with vertex F. So vertex F is located at -3, 4. Write that down here. And if F prime is located at y negative x, then F prime will be located at 4, 3. Let's go ahead and plot this at 4, 3. And this is where F prime will be located. Now let's connect these vertices to form the sides. So we've created a new image after rotating triangle DEF. Remember that it's not just the vertices that were rotated, but every single point on the figure. Let's draw distances between each vertex on the pre-image to the center of rotation, and distances between the center of rotation to each vertex on the image. So we'll draw a distance from E to the center of rotation, and then the center of rotation to E prime. We'll draw one from D to the center of rotation, and from the center of rotation to D prime. And then from F to the center of rotation, and then the center of rotation to F prime. Now note that these distances we drew all seem to form 90-degree angles. This is because a rotation of 270 degrees counterclockwise is equal to a 90-degree rotation clockwise. What is the pre-image of the figure if the rule that created the image is a rotation about the origin with an angle of rotation of negative 90 degrees? So we know that the figure shown is an image after a rotation. We have to find the pre-image, or the original image, before the rotation. Notice that according to the rule, we are rotating by a negative number of degrees, negative 90 in this case. When given the image, we have to undo the original rotation, so we must go in the opposite direction of the given rule to find the pre-image. If the image was the result of a rotation of 90 degrees clockwise, because negative degrees indicates a clockwise direction, I need to move 90 degrees counterclockwise to undo the transformation. So using this idea, the pre-image should be approximately located around here. The rule for rotating 90 degrees counterclockwise is this. Where if we have a coordinate at xy, that's being mapped to negative yx, where xy are now the coordinates of the points on the image. So if q prime is located at 5, 2, then we use the rule to map q to negative 2, 5. So let's go ahead and plot q at negative 2, 5. Okay. Now if r prime is at negative 1, 2, then we can use the rule to map r to negative 2, 1. Negative 2, negative 1. And now we can plot r, which is going to be at negative 2, negative 1 here. And if s prime is at 2, 4, then we can use the rule to map s to negative 4, negative 2. And if we plot s, we're at negative 4. I think it should be negative 4, positive 2. Okay, so negative 4, positive 2. And then we plot s. Remember, you could also draw angles of 90 degrees for each of the vertices if you forget the rule. Now we can connect vertices to create the triangle.